When you think about massive companies like Netflix or Amazon, have you ever stopped to wonder how they know, like, the instant something goes wrong with one of their millions of servers? Well, today we're going to pull back that curtain. We're going to dive deep into the world of server-side monitoring and actually architect a system from the ground up. The goal? To get a crystal clear view into a sprawling global infrastructure.
All right, so let's get right into it. Because when you're running a massive distributed system, a tiny failure in just one component, well, that can trigger a total cascade of crashes across your entire application. And just, looking at individual server logs, that's not going to cut it. Finding the real root cause is a huge engineering challenge, and it absolutely demands a dedicated solution.
Okay, first things first, we've got to define the problem space we're working in. I mean, monitoring a single computer, that's simple, right? But what happens when your infrastructure spans multiple data centers with thousands, maybe millions of servers? The truth is, something is always failing somewhere. The real challenge, the whole point of this, is getting that bird's eye view over all that chaos so you can spot problems before they ever impact your users.
So to get that view, you need to think in layers. A truly robust system has to see everything. You start at the server level, right? Watching for things like CPU spikes or disk latency. But then you have to go deeper, to the hardware itself. Are memory modules failing? Are disks about to die? Then you zoom out again to the data center infrastructure, the switches, the load balancers, and finally you zoom all the way out to global service health. We're talking DNS, cross-region latency, peering points. This is what we mean when we talk about true observability.
All right, so now that we've got a handle on the problem, let's start architecting our V1 blueprint. What are the absolute must-have core components we need just to get a basic system up and running?
And here it is, our starting point. It's a beautifully simple loop. On the left, you've got your services and servers, just generating all these metrics. Then our data collector service, think of this as the workhorse of our system. It gathers all that data and funnels it into a time series database. A TSDB is really just a specialized filing cabinet, one that's built specifically for time-stamped info. And finally, a querying service lets us ask questions of that data, maybe through an API or, more likely, a visual dashboard.
Okay, now we hit our first major architectural challenge, storage. A system like this is going to generate a relentless, absolutely massive fire hose of metric data. We need a really smart way to handle all of it. And here's the crucial point. Not all data is created equal. The metrics you need for a real-time dashboard, what's happening in the last 15 minutes, that has totally different requirements from the data you need to do a deep dive forensic analysis 6 months from now. It's those access patterns that have to dictate our storage strategy. So the solution is pretty elegant, a two-tiered storage system. For our hot storage, we use that high-performance time series database we just talked about. It's optimized for lightning-fast queries on recent, super granular data. But man, keeping all that data in hot storage would be crazy expensive. So for long-term archival, we shifted over to cold storage. Think low-cost, durable blob storage. This gives us the perfect balance of speed when we need it and affordability for the long haul. But, just collecting data isn't enough to actually prevent an outage. We need a system that can do something about it. That's where the rules and action database comes in. You can really think of this as the brain of our entire operation. It's what stores all the logic that maps a specific metric threshold to a predefined automated response. Something like, hey, if CPU on these critical servers goes over 90% for 5 minutes, trigger a high priority alert to the on-call engineer.
Okay, so we have a place to store our data, and we have a brain to make decisions. But how do we actually feed the beast? How are we going to collect all those metrics from thousands, maybe even millions of servers scattered all over the globe? And this brings us to a classic architectural crossroads, the push versus pull debate. Do we have every single server constantly pushing its metrics to our collector? Or does our collector actively reach out and pull or scrape the metrics from each server? This is a really critical design decision, and it has huge implications for network traffic, for reliability, and for the complexity of the code on our application servers. For our initial design, we're going to go with a pull strategy. And here's why. It gives us centralized control over how often we collect data, which is absolutely crucial for managing network load. It also makes our application servers way simpler. They don't need all this complex logic for retries or batching.
Now, we have to be honest about the trade-offs here. A purely pull-based system can introduce its own problems, like creating a potential single point of failure, or SPOF, in our central collector, and you can definitely hit some scalability ceilings. And look, this isn't just some theoretical choice we're making. It's been proven to work at a massive global scale. Take a company like DigitalOcean. They use this exact pull-based approach to monitor millions of machines all over the world. It really demonstrates the power and the scalability of this model. All right, so our system can now collect and store data using a pretty robust pull model. But there's a problem. In modern cloud environments, your infrastructure is never static. It's completely ephemeral. Servers, containers, services, they're constantly being created and destroyed, sometimes in minutes. And that presents a huge operational challenge. I mean, can you imagine having to manually update a config file every single time a new server spins up? Your monitoring system would always be out of date. No, the only real answer here is to automate the process of finding what to monitor. We need what's called dynamic discovery. And for that, we introduce a brand new component, the Service Discoverer. This thing is literally the eyes of our system. The way it works is simple but really powerful. It integrates directly with the APIs of platforms like EC2 or Kubernetes or Consul. And it just asks them, hey, what's running right now? It gets back a dynamic, real-time inventory of every target that needs to be monitored. Zero manual intervention required. Okay, let's put this all together. Let's trace the complete life cycle of a single alert. So step 1, the Service Discoverer finds a new server. Step 2, our data collector gets notified and immediately starts pulling metrics from it. Then, the server's disk I/O suddenly spikes, and that violates a threshold that we've stored in our rules database. The querying service, which is constantly checking these rules, detects the violation and tells the alert manager to fire. And finally, the alert manager shoots a notification straight to an engineer's Slack channel. See that? It's a fully automated, completely seamless flow. And here it is, the whole shebang. This is our final architecture. You can see how it all connects. From the Service Discoverer automatically finding new targets, to the data collector pulling metrics, our super efficient dual storage system, and all the way through to the rules DB, the querying service, the alert manager, and finally a dashboard for visualization. What we've designed here is a complete automated observability platform. It's powerful enough to drive everything from simple line graphs to even complex 2D heat maps, which you could use to visualize an entire cluster's health at a single glance. So what's the big takeaway from all this? Building a robust monitoring architecture like the one we've just walked through, it's the absolute foundation for reliability. But let's be real, the system we've designed here is fundamentally reactive. It tells us when something is already wrong. The true next frontier, the really exciting part, is using all this data for proactive, predictive analysis. How can we find the signals in the noise that let us predict and prevent failures before they ever happen? And that, well, that's a fascinating challenge for another day.